And in this video, I'm gonna give you lectures on topic 3 and topic 4 together. So regarding topic 3, stress concentration, I don't have much to say because we have already covered this concept in axial loading chapter. So here the only difference is that in axial loading chapter, we considered a sort of plate geometry, like this geometry with radius curvature R and the width D, and here with large D. But instead of this structure here, we are considering circular shaft. Okay, so please have the distinction between circular shaft problem here and this sort of thin plate problem. Okay, but anyway, other than this difference, we have like a mathematical similarity here in torsional loading chapter. So we have three-dimensional parameters: large D, size of the gear, and small d, the diameter of the shaft, and r is the radius of the curvature at the joint. Okay, and we are considering stress distribution here. If we don't have any this kind of undulation of the diameter, we're gonna have the distribution we obtained in previous section for uniform shaft. However, due to this undulation, we're gonna have higher stress at this point. Okay, and that stress must be obtained by stress concentration factor K and tau max of diameter D cylinder here, like a maybe far from this joint, due to the Saint Venant principle and others, we're gonna have uniform and non-uniform, the distribution equal to the constant cross-section shaft, and we can obtain the tau max for that diameter, which is CT over J. And if we multiply the K stress concentration factor, we can obtain maximum stress here, and this maximum stress must be smaller than allowable stress. Okay, so that's the logic behind this. And how do we obtain the K? Of course, for like a simple geometry, we can obtain this from analytical solution. For more various ratio of large d and small r and small d, then we can use computer simulation to obtain the stress concentration factor K. And actually we can find the table from our textbook. Okay, and this factor K is function of large d over small d. When we have a larger and larger d over d ratio, we're gonna have higher K. And regarding the small r and small d ratio, when we have smaller radius curvature, we're gonna have higher concentration factor, and that's it. Okay, of course, when r becomes 0, stress concentration factor will be infinity. Of course, we cannot have r is 0 because the world and real material made out of atom, and atom have radius, right? So we cannot have 0 radius. Anyway, so by looking for large d over small d ratio and small r over small d ratio, you can find the stress concentration factor, and using this factor you can obtain the solution for safe design and reliable design. Okay, so with that, let me finish my very short lecture on topic 3, stress concentration. And as a final lecture for torsion loading, because we're gonna skip the video lecture for topic 5, which is plastic deformation, let me give you torsion of the road with non-uniform cross-section or non-uniform non-constant torsion T. Okay, so first we're gonna consider non-uniform cross-section. Second, we're gonna consider non-uniform non-constant torsion T. Okay, so the problem we're gonna first consider, the example we're gonna first consider is a road with non-uniform cross-section, and here the cross-sectional area is keep changing. Of course, as I told you, even though I say that non-uniform cross-section, we have to only consider circular cross-section. If it's not circular cross-section, we're gonna be in trouble, and we cannot apply our knowledge. Okay, but anyway, for this problem, let's consider like this is small section with length delta x. Then the twist angle within that section delta x can be written as delta phi, and delta phi and delta x ratio can be obtained as t at this specific position x and divided by g and j at this specific position, because j is also changing because cross-sectional size is keep changing as a function of x. Okay, now after obtaining this delta phi and delta x ratio in terms of tx and jx, we can obtain the torsion angle from this wall to here using this integral equation. Simply we do integral for this guy, and this guy is t over gj multiplied by dx, which is the expression in the integrand. Okay, and we have to do this integral from 0 to L. Now for this problem we have applied torsion T at the tip of this pillar, and wherever point you have or wherever section we are having as an imaginary cross section, we're gonna have the same torsion T. Okay, so in this problem, our answer will be simply T over G Jx dx, and Jx would be determined by this curve. Okay, or the under the size of this radius. Okay, and we have went through a similar example for axial loading chapter. In axial loading chapter, we considered delta divided by delta x can be written as n over ea, and to obtain the delta for entire rows, we have to use this integral, and that was the example we have gone through in axial loading. Okay, so this example seems too simple, so let me give you a little bit more complex example. So in this example, instead of having just one single large torque, we're going to consider distributed torque over the entire surface. So, and this distributed torque is typically denoted as small t in our textbook, and suppose that this t is uniform. Per unit length per meter, we are applying 1 Newton multiplied by meter torque for each surface. This is can be considered as like a distributed torque, which is same value per unit length over the entire domain. And the mathematical analogy and mathematically analogical problem in axial loading was actually this problem. And why is it so? We can answer why they are similar problem by drawing free body diagram. Okay, so let's take a x as the origin at the wall, and let's take some imaginary surface x point, and the other area will be L minus x. Okay, so if we take this area as imaginary surface and try to draw free body diagram, it will look like this. So there is distributed loading within this zone, and this distributed loading must be balanced by the reactions at the cross section. Let's say this is unknown cross section tx. Okay, and the length here is the torque per unit length is t small t. So if you multiply torque per unit length and the length L minus x, it will give you the torque acting on the entire volume. Okay, and to make a balance as a reaction at the cross section, we need this much of torque. If we use double arrow notation, we're gonna have this distributed loading over the entire surface, and as a reaction, we're gonna have this green thing on the cross-sectional area. Okay, then at x point, delta phi and delta x can be written as this expression, tx divided by gj. Here j is constant over the entire pillar. Okay, now the problem becomes a little bit more interesting. Now t is function of x, and which can be written as this. And if you plug this expression and obtain the solution, we end up having the total twist angle is the same as small t over gj and L square over 2. Okay, so this is the final answer. And even more interesting comes if we try to visualize the deformation. So suppose that before the application of the torsion, we have like a line on the surface. Okay, after the torsion, this line will move to here, with angle phi. But what about the line between the wall and here? Okay, so we not gonna have same and not gonna have a straight line for this problem because we're gonna have different torsion t at different x point, and we're gonna have different rate of change. Okay, the rate of change of this twist angle delta phi and over delta x different, and actually it's largest when it's near to the wall. It becomes smallest near to the end point, because near to the end point we have a very small section of this distributed loading contributed to the reaction at the surface. But here near the wall we have to balance out the entire distributed torsion over the beam. Okay, so the slope delta phi delta x is largest here, and delta phi delta x is smallest here, and it will be almost 90 degree at the end. Okay, so this is the visualization of the formation of the twist angle, and this gives us like another interesting example problem. Okay, but one thing I can just tell you for this torsion chapter is, please try to understand and please try to visualize like what kind of deformation is occurring for that problem. That's the first thing you have to do. However, of course, getting good score in homework and good score in midterm is important. So to get good score in homework and in midterm problem, you can simply replace the problem and rewrite the problem using the double arrow notation. Then you're not gonna have any trouble in determining sign convention and etc. And you're gonna get very nice score. Of course, if you don't have good understanding, if you don't have good imaginary visualization in your head and just rely on this, you're not gonna get 100% out of this torsional loading chapter. So of course it's okay to use double arrow notation for homework problem, but as an engineer, especially like a structural engineer, please try to visualize what kind of deformation is occurring for entire body that you are studying. Okay, so that's the advice I want to give you, and let me finish my video lecture here. Regarding the topic 5, if you are interested in, please take a look, but if not, never mind. Okay.